Good afternoon, everyone. Can you all hear me? Great. Okay, there we go. Okay, so today I'm going to continue the lecture on digital control theory basics. I noticed that only a few of you have taken the quiz, so I'll give you some time, a little bit of time here at the end of the lecture to go and take the quiz. Remember that quiz is due on Monday, and that will cover the remainder of the interfacing lecture, mostly on I²C and the multi-slave SPI. Okay, so last time I started talking about control systems. Control systems are important for cyber-physical systems, which is when you have a controller, a microcontroller, a CPU of some kind that's exerting control over the physical world in some way. So I gave you some examples of that, like it obviously comes up a lot in robotics and in power electronics, I mentioned. So things like robots, drones, and DC to DC converters. There's also, of course, self-driving cars, cameras, and thermostats, like the smart thermostat, although that's a low-speed system. So I mentioned there's three different ways that you can do control. You can do passive control, like with these trucks, where you put features on them to try to control the drag, the aerodynamic drag. There's also open loop control, which is where you have a controller connected to a plant, where the plant is the thing that you're controlling, usually some sort of device. And the controller takes an input and then sends a control signal of some kind to the plant, but then there's no feedback, so it's open loop. Open loop systems are fine if the plant can be modeled perfectly. Then you don't need a feedback. The only reason to have a feedback, which is what you have here in a closed loop system, where you have a feedback coming from the output of the plant, kind of feeds back, and you take the difference between the output of the plant and the set point. So you see over here, there's a summation block that takes the what I want and what I'm getting, and takes the difference of those two, which becomes the error term, which is fed into the controller and then used to calculate the control input for the plant. This is a closed loop system, and closed loops are for plants that are subject to disturbances or uncertainty. So if you have a drone, for instance, and a gust of wind obviously will affect it while it's flying, and that would be considered a disturbance. So you'd want a closed loop system for something like that. Also, if you have a plant that's a complex system, like for example, when you're designing a controller for a robot, or even just like a cruise control system for a car, you can't accurately model it, and so because the model is an approximation, you need the feedback in order to control it. So I mentioned that in this class we're going to be using linear time invariant systems to describe the behavior of the plant and the controller. These are fairly simple ways to do modeling. It's basically a differential, partial differential equation, but it's not any partial differential equation. It's a very limited kind of subset of partial differential equations. And most notably, they are linear, as it says right in the name. And as it turns out, linear, no physical system in real life is linear. In fact, everything is nonlinear. And so a linear time invariant system is by definition is an approximation of a physical model of something. So for instance, if you have even a very simple device, like you have a spring will have linear behavior as you stretch it out and compress it until you reach the limits of how far you can go. I mean, eventually, if you stretch a spring long enough or stretch it out far enough, it'll break. And if you compress the spring, eventually you'll reach the limit of how far it can be compressed. At which point it stops behaving linearly. You have kind of like these limits. And the same thing happens with a drone, because if you have a rotor on a drone, you have a control input that will allow you to speed up or slow down the rotor, which it acts fairly linearly until you get to the point where you've kind of maxed it out. You've sent it the signal that makes it spin up to its maximum speed, at which point you can continue sending a higher input signal into it, but the rotor will have some maximum RPMs that it can't exceed, and so it's a nonlinear system at that point. So oftentimes the LTIs are designed to approximate kind of devices that are operating in their linear region. The nice thing about LTIs is that they're simple, and you can compose them into you can take LTIs. They're kind of building blocks, basically. You can take them and you can build up. You can connect them together in with arbitrary connections, and you can form a more complex system. So in that sense, it's kind of like digital building blocks in a way. Like in 611 course, you can have modules, digital modules. You can connect them together, and LTIs are work in a kind of a similar way. So a linear time invariant system has in input and output signals. I mentioned that it's the reason it's called linear is that it's a differential equation that's linear, where you can basically add together functions or derivatives of functions or integrals of functions, and you can multiply those by a constant scalar. But that's it. Those are the rules that you have to follow. They also have a frequency response. You'll see this a lot. We're not going to be talking much about frequency response in this class, but you're familiar with frequency response from Electrical Engineering 222. And so if you have a linear one of these LTIs, you can characterize its frequency response and its input signal. So its output will always have the same frequency as its input, but you'll get a different phase and amplitude depending on the frequency, the input frequency. So it won't change the frequency from the input to the output, but it will respond to different frequencies by manipulating the phase and the amplitude that's used to change the input signal. So yeah, so it's similar to the types of systems you looked at in Electrical 222. It's also time invariant, which means that the output signal doesn't depend on the time. It only depends on the input signal. If you have the same signal coming in, it doesn't matter if you were to time shift both the input and the output signal simultaneously, you'd still get the same result. And then an LTI can be described as being stable or unstable, and stability is really the goal of control theory, is to take an unstable system and make it stable. And I'm going to talk more about that in a minute. And LTIs are also described by their transfer function, which is essentially kind of how you get an output from an input. Okay, so let's look at an example. So I literally just made this up. You notice that is an equation here. I've got two time series functions u and y, so u of t and y of t. And then on the right hand side, I have in addition to just y of t, I'm also adding to that the derivative of y of t with respect to t, and then I'm subtracting 6 times the integral of y of t, and that would be starting at time 0. LTIs typically start at time 0. So you'll notice that basically the bottom line here is I've got two functions. They're both functions of time. They're both time series functions, but I'm basically treating them like I would just a regular variable if this was a regular linear equation, right? So if if I had a regular linear equation and I had just variables instead of the functions of t, functions of time, then this would just be a linear equation, a regular linear system. And that's really what an LTI is, except instead of having variables in there, you have these functions. Now notice I have two, because the objective here, so there's u and y, and the objective here is to create a transfer function that will relate one signal to the other. So by itself, this equation is describing the dynamics of u and y. But it doesn't necessarily have an output or an input per se. It's just an equation. Now, LTIs are always described in not in the time domain, but in the S domain, the frequency domain. So hopefully you remember this also from your electrical engineering course, your signals and systems. And this is really not really as complicated as you might think. Basically, all you do is when you have an LTI like this, in this form. So remember, I said an LTI is just some functions of t, and then you can take the derivatives of some, or the integrals, or the double derivative or double integral. But and then you can add scalars in there, and that's really all you can do. And so in that form, it's really trivial to convert it to the S domain, to the Laplace domain, because all you have to do is everywhere you have a derivative, you multiply the function, you drop the derivative notation and just multiply by S. And when you have an integral, you multiply by S over S, well, 1 over S, or S to the negative first power. And then the constant scalars just remain in there, and then it becomes a function of S instead of t. And notationally, you also capitalize the names of the functions. So notice that at the top I have lowercase u and lowercase y, and then I made them uppercase u, uppercase y. That's just a convention that people generally follow. And then instead of t, it's of s. Now s is a complex variable, and it represents the transient and steady state response of the function, but that's not really that important. The only thing that you need to understand here is that how to just do this simple conversion from the time domain to the frequency domain for an LTI. So this is basically taking the Laplace transform. Okay, so now you want to build a transfer function. And the transfer function is really what is the point at which you start to define what the inputs and outputs are. So even in the Laplace domain, you basically just have an equation that's describing the dynamics between these two signals. But when you put these into a transfer function, that's when you start to kind of conceptualize this as a block that you can then put in a block diagram, like a component, a module. And so the way that you do that is you solve the equation where you put you take the equation and you put it into a form where the output of the LTI, well, I should say of the transfer function that represents the LTI, is in the numerator and the input is in the denominator. So in this case, I want to come up with y of s over u of s. So at this point, I just have to use some simple algebra, to do that. So so for instance, to do that, I can take the right-hand side of the equation and I can factor out y of s, because you see that all the terms on the right-hand side are multiplied by y of s. So I can say y of s times, and then in parentheses, 1 plus s minus 6s to the minus first power. And then I can divide both sides by u of s, which will give me y of s over u of s on the right-hand side, and then divide both sides by 1 plus s minus 6s minus 1. So basically I took this part and I brought it over to the left. I took the u of s and brought it over to the right, and then I swapped both sides so I could get y of s over u of s on the left-hand side. So now I've got a fraction, 1 over 1 plus s minus 6x to the minus first power. See, I heard a ping. Yes, you will be tested on the Laplace transforms, but only in this form. You don't have to worry about doing more complex Laplace transforms. So, like I said, this is trivial. This is literally just converting the derivative to s and the integral to 1 over s. That's all we're doing here. So this is not, obviously there's much more complex ways that you can do Laplace transforms, but because we're dealing with these LTI systems, which are kind of simplistic equations, it's not hard to do. So that's all you're going to have to do for this. There is an inverse Laplace that we're going to do, and I'll show you how to do that. We're going to do the simplistic form of that as well. Okay. So now let's switch gears here for a minute and talk about stability. So the definition of a stable LTI system is a system that will always give a finite output for any finite input. Now, that doesn't necessarily mean that there may be inputs that you can give an unstable system that will still give you finite outputs. But generally speaking, in more general terms, when someone says a stable system, you generally assume that it is a system that if you don't provide it an input, or actually if you give it a constant input, that the system should kind of settle into a steady state, it should converge on some output, as opposed to kind of oscillating and kind of blowing up, diverging. So to kind of give you an idea of what I mean is, imagine one of the classic examples of a control system is an inverted pendulum, which is where you have, imagine you have a car, like a little remote control car, and you have a pendulum that's sticking up from it with a weight on top. And the goal is to drive the car back and forth, just in one dimension, so you can go forward or backwards, but do it in a way that will balance the pendulum upright. So make small movements to keep the pendulum upright, because if the car were to stop, not move, the pendulum would just fall down, right? And in fact, the human body is actually an inverted pendulum. It's because, you think about it, in order just to stand and walk around, you have to constantly, kind of make control decisions. You have to stay upright and balance yourself. If someone were standing and they suddenly went unconscious, of course, they just fall on the floor. And so that's kind of the idea, is that the pendulum by itself is unstable. It needs to be stabilized by a controller. Sorry, go ahead. Someone say something? No? Okay, sorry. Maybe someone left it. Okay, so I have a picture of an F-16 fighter on there too, because the F-16 was the first mass-produced airplane that is inherently unstable. Most airplanes are stable, at least like small scale planes, simpler ones, where, like if you're flying and you let go of the controls, the plane will just fly straight. Now that's assuming, of course, you have you have to trim the the elevator, otherwise you'll start to go down or up. But as long as the airplane is assuming it's trimmed out, the control surfaces are trimmed, you can let go and it'll just fly straight. In fact, you can even bump the control, the yoke, and when you first bump it, the plane might go down or up, or it may bank to one side or the other, but it'll eventually just by itself stabilize out and go straight. Whereas the F-16 was designed to is actually inherently unstable. If you're in an F-16 and you didn't have the benefit of a computer that's controlling it, if you just had direct control over it, the pilot had direct control, then holding the stick straight wouldn't make the plane fly straight. It would go out of control immediately. And so they have a controller in there that actually sits between the pilot. So the pilot basically gives the controller a set point, and then the controller is constantly making small adjustments to all the control surfaces to keep the plane flying straight, or to do what the pilot wants it to do, follow to the set point. So that plane is unstable the way that the airframe is and the control surfaces are designed. So it has a controller, and they did that to make it more maneuverable. Now, how do you know if a system is stable or unstable? As far as I know, there's 3 different ways to do it. You can, and one way to do it is to use to hit it with an impulse function. So if you have a system and you inject an impulse, a unit impulse, which is an input that goes from 0 to 1, and then back to 0 for an infinitely small amount of time. It's called the unit impulse function. Now, generally, the way you would do that is you would apply the impulse in the S domain, and then you do the inverse Laplace transform, and then you would then plot the signal, the output, in the time domain. And it turns out that the impulse response in the Laplace domain is just 1. So it's just a constant. There's no S in it, unlike other types of sources that you would inject in. Oh, sorry. Yeah, hold on one second here. Sorry, thank you for telling me that you can't see the slides. I don't know what's going on. So I am sharing. Okay, hold on. Let me just reshare. Sorry. I went from, the only thing I did was went out of presentation mode and back, but maybe that confused it. All right, reshare. Okay, hopefully you can see them now. Can you see them now? Okay, cool. Okay, now I'm going to go back into presenter mode, and hopefully I don't lose you. Okay, so you can do the impulse response in the time domain, basically. The other way that's actually more common, and this is the way that we're going to focus on in the class, is to find the poles of the transfer function. The poles are the values of S that would make the denominator 0, meaning that you would get an undefined value in there, right? So in other words, the values of S that would give you a divide by 0 error. Those are the poles. If those poles, now I mentioned that S is a complex variable, so you could think of a complex value has a real and an imaginary part. If you were to plot the imaginary part on the y-axis and the real part on the x-axis, then as long as all the poles are on the right-hand plane of the plot, meaning that they all have real values that are less than 0, not 0, but less than 0, they got to be negative. So if they're all negative, they all have negative real parts, then it's a stable system. And then finally, the third option is you can simulate the system using an impulse or a step or a sinusoid input. So if you simulate it in software, you have more options in terms of what input source to use. So you could do that, and we're not going to be doing that because I don't want to get embroiled in the software for this class. I just want to give you kind of just the introduction to this stuff. But I'll show some pictures of that as we go along, so you can see what the simulations look like. Oh, okay, yeah, got it. Okay, so yeah, so I'll show you the axes here in just a second. Okay, all right, so I'm gonna go back to presenter. Hopefully, I don't lose you. Okay, so let's go back talk about that impulse again. So the unit impulse signal is also called I think it's pronounced Dirac delta, um, which is shown as a delta, lowercase delta. And the cool thing about the Dirac delta is that in the S domain, the function is one. It's just the constant one, meaning that it doesn't have any s inside of the it's delta of s, but is delta of s equals one, right? So there's no s on the right hand side. Um, Dirichlet delta. Okay, thank you. Okay, cool. Dirichlet. Thank you, Charles. Dirichlet delta. Um, so yeah, so it's basically just one. And so now I haven't mentioned this yet, and I'm going to talk about this just in a minute, but when you have a transfer function and you want to plug an input into it, you basically just multiply. You multiply the two transfer functions together, and this is why we do it in the S domain. But you know, if the delta is if the delta is 1 and you're multiplying it against a function, then you're just multiplying it by 1, right? So what that means is that all transfer functions are actually just the impulse response. That's the way that, you know, so they're kind of, you kind of get it for free. In other words, if you have an S domain transfer function, it's the Dirac response. So basically, I have a picture there on the upper right hand corner. Shows that thing. So it's an impulse. And then some people also use the step function as well, which is where you go from 0 to 1 and you just stay at 1 at time 0. It doesn't have to be at time 0, but you know, typically you see the impulse happen at time 0. Now you might be thinking, wait a second, why are we using these two inputs? Like it's kind of strange to use these inputs. Well, the reason is because the impulse and the step actually include all of the frequencies. So basically, in order, like if you're taking sinusoids and adding them to get some, you know, to get a signal, and you're trying to add them together to get one of these two shapes, you'd have to add you know, basically an infinite number of frequencies together, infinite number of sinusoids together. So this includes all the frequencies. That's why one of the reasons why it's nice, because it allows you to basically hit a function with all the frequencies. And the reason for that is because you can actually have a transfer function that looks like it's bounded with one frequency, but it's not bounded for another. So it might, you know, you may have infinite gain at one frequency but not in another. So that's one of the reasons why these two are used, the impulse and the step function. So if you have a transfer function, so here's the transfer function that we just built, that I just made this up, you know, this one. This is the y of s divided by u of s. So y is the output and u is the input, and they're in the S domain. Now, one of the things here is that you have to keep in mind is that oftentimes when you have a transfer function, they are abbreviated. You might just see y over u without the s at all, or even more commonly, you'll just see y. You'll just see like they'll drop, you know, there's a shorthand where you can drop the y over u. So keep that in mind as well. But in this slide, I'm showing y of s over u of s. And so we have this fraction. And so now in this case, I want to put it into the standard form. So the standard form is to have the denominator be to be a polynomial, where the smallest power of the polynomial is 0, right? So in order to do that, I can just multiply this transfer function by s over s. So I end up with s over instead of 1, that becomes s. Instead of s, that becomes s squared. And then the minus 6 becomes just minus 6. Or the minus 6s to the minus 1 becomes minus 6. And then I can rearrange that into a proper polynomial order, second order polynomial. So s squared plus s minus 6. And then I can factor the polynomial into s plus 3 times s minus 2. Just using, high school algebra. And now I can find the poles. So this transfer function has two poles. It has one at -3 and one at 2. So because if I put if s is -3, then I'll get a divide by 0, and if it's 2, I'll get a divide by 0. So generally, you would show that using a pole 0 plot, which is just a regular Cartesian plot where the real is on the horizontal axis and imaginary value is on the vertical axis, which is pretty standard. But then the poles would be marked as x's, and the zeros, which is where the values of s that would give you a 0 value as opposed to an undefined value. So basically, if you factor the numerator and find out where you get your zeros, that would be shown with just circles, which in this case we have a 0 at s equals 0. But we don't care about zeros for the purpose of this lecture. We only care about the poles, because the poles are going to tell us about stability. So in this case, we have a pole at -3, which is in the right-hand plane, but we have also a pole of 2, which puts it in the I'm sorry, left-hand plane. Sorry, if the first pole -3 is in the left-hand plane, it's on the left side of the vertical axis, and then the 2 is on the right-hand side plane. And so because we have that +2, because we have a pole that is not in the right-hand plane, meaning that it is, has a 0 or a positive real value, then that means that this is an unstable function. So how do we check that? Well, I mentioned that you can hit it with an impulse to find out. So how do you do that? Well, we have to convert this back to the time domain. So we have to do an inverse Laplace transform. And in order to do that, well, basically the way you do that, generally speaking, is you just look at a table. But the problem is the table has kind of these different forms, and then you have to match those up and then kind of translate it. So in order to make this work, you look at the table and you see that there is if you have a 1 divided by s minus a, the Laplace, the inverse Laplace transform of that is e raised to the at. So the problem is that we have to get this function in this form, the 1 over s minus a, or a sum of those things, which means that we have to decompose this function, this function, into terms that look like this one. So one way to do that is, and this is assuming that we have, this doesn't work, but what I'm about to show you is not going to work if we had the two poles that were the same. But as long as you have distinct poles, you can do a thing where we can decompose it, where you have the original function, which is s over s plus 3 times s minus 2. And we want to decompose that into, we want to basically split the denominator into 2 halves. So a over s plus 3 plus b over s minus 2. So, so to do that, we will basically pretend as though we started out with a over s plus 3 plus b over s minus 2. If we started out with that and we wanted to merge those two guys together, then we would take a and multiply it by s minus 2, and we take b and multiply it by s plus 3, and that would allow us to have combined them together, right, into one fraction where we had the denominator was the product of the two denominators, right? So this is if like I said, if we had started with this, we could merge them by doing this, right? Okay, so then that means that we have, if this gives us the same denominator on both sides of the equation, so we can say we can just basically multiply both sides of the equation by that denominator, and we're left with s equals a times s minus 2 plus b times s plus 3. So if we can solve for a and b, then we'll have a and b, and we'll be able to decompose the function. But it's a problem because we have two variables and only one equation. So so how do we fix that? Well, if we assume for the moment that s is 2, let's pretend that s just equals 2. That would actually knock out one side of this. It would kill the a variable because you have a times s minus 2. If we just pretend that s is 2 for a moment, then that would be 2 minus 2. We'd end up with a times 0 here, right? And then on the other side we'd have b times 2 plus 3, or 5b, right? And then we can do the same thing with the b side, where we can pretend that s equals -3, and that would effectively eliminate the b side. And then we'd end up with -3 equals a times -3 minus 2, right? And then we can solve for those guys. So in this case, this would be 5b equals 2, so b would be 2/5, right? So I substituted that in for b over here. And then over here I have -5a equals -3, so a would be 3/5, right? So then I take 3/5 for a, I drop it in here to where a was up here, and then 2/5 for b, and I drop that into where b was. Now you can imagine that if the denominator was like, say, s plus 3 times s plus 3, then this approach wouldn't work. That you'd have to, there's another way you can approach this, but this is the simplest form where each of the poles are unique, and this allows us to decompose this into this form. Now once we have it in this form, now we can do an inverse Laplace transform, because we have this, we can go to the table of inverse transforms, and we see that if I've got 1 over in this case, well, 1, I don't have 1, I have these scalars, but that's okay because I can move those scalars out when I do the inverse Laplace. And then I've got s minus a, and then I've got, of course, a. In this case, the a would be -3, and in this case, the a would be 2, right? So so what that gives me is, if I take points, so I end up with 0.6 divided by s plus 3 plus 0.4 divided by s minus 2. That's just I took the fractions out. And so then I do the inverse Laplace of that. I end up with 0.6, so I bring the 0.6 out, and then that gives me 1 over s plus 3, which you would convert to e raised to the 3t power, right? So according to this table, it's kind of low res, but so you take the a and you bring it up to the exponent, multiply by t, and you add, this would be 0.4 times e to the -2t. Okay, so that is the inverse Laplace, not of the whole, well, of the transfer function, but in particular, that's giving us the inverse Laplace of the impulse response, because the original impulse was the input that we multiplied, and again, I didn't talk about that. I'll come back to that in a minute, but we basically multiplied the Dirac impulse with this guy. So we end up with this function. So then you just would plot this function over time, which I did here. I just plotted this in MATLAB real quick, and I should have started plotting that at 0, but for whatever reason, the x-axis starts at 1. That's the way I set it up. But the point is that you can see that if you plot this function, it's unbounded in the sense that it starts out small, and then around between 8 and 9 here, it just zips off into it. It just shoots upward. So this is unbounded. This just goes up to infinity. And so this is the impulse response of that transfer function. would it not be e raised to the minus 3t? I might have switched it. Points 3 minus 3t. Yes. Yes. Did I screw that up? Yeah, because that's 3. That would be negative 3, right? Yeah, I think I did screw that up too. Yeah. 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 Hopefully I didn't. Hopefully that doesn't. Hopefully when I plotted it was right. Unless but I transcribed it wrong from here. Yeah, s plus 3, s minus 2. Yeah, so the a is negative here. It's positive there. So negative 3 plus 2. Yeah. Yeah. Um, yeah. Yeah. I think that it should still be unstable though. I might have to redo the plot. Okay. So so I mentioned that you can also simulate. If you go into MATLAB Simulink, you can simulate other inputs, not just the impulse response. You can also look at the step response too. So I went ahead and I did that because it's easy to do in Simulink. You literally just go into Simulink, you drop down a source, and you say, I want a step source. And then you drop down a transfer function and you tell it what the coefficients of the polynomial are for the numerator and the denominator in the S domain. And then on the other side, you can put a scope. So I attached a scope to the output of the transfer function, and I attached a scope to the output of the step function, which I'm not showing that here, but I'm showing the results of the scopes here. So the step function in MATLAB, and I don't know why they do it like this, but the step function actually goes from 0 to 1 at time 1. So this is simulated for 10 seconds. And at 1 second, we step. In this case, it doesn't really matter when you step. I mean, it'll if you step earlier or later, it'll change the output. It'll phase shift the output a little bit. But in generally speaking, you know, they start out at 1. They do the step at 1. I think you can change that, but anyway, you can also step at 0. The point is that if you look at the output, you get this. It kind of starts out, you know, oscillating here a little bit, starting at 1, right? So starting at 1 second, and then it just you get this you get this sine wave that just blows up, and it diverges. So I only showed it. I simulated for 100 seconds too, but take my word for it. This thing just keeps growing and growing and growing. Just for the heck of it, I also put a sine wave into it as well. So I just stuck a sine wave in at 2 radians per second sine wave. And the reason I chose that particular frequency was because that was where one of the poles was at 2 radians per second. But actually, and after this, I tried different frequencies and I got the same result. It blows up. Same thing happens here. So you put a sine wave in, and it just goes crazy. It diverges. It is unbounded. So what about a stable function? Well, that should be easy to test, because all I have to do to get a stable function is go back to my original one and change it so the poles are negative, right? So all I have to do is take the original fraction, and so it's s divided by s plus 3 times s plus 2. So this way, I now have poles at -3 and -2. So they're over here on the left-hand plane. And so this should give me a stable function, but I can test it by going through the same steps I did before. So once again, I'll take this guy and decompose this function into a sum. So again, I say this equals a over s plus 3 plus b over s plus 2. So, you know, basically breaking up the s plus 3 and the s plus 2 into 2 separate denominators, and then I solve for a and b by just choosing s values that, knock out A or B. And that way I end up with, one equation and one unknown. So in this case, B is -2, A is -3. And so I'll get a transfer function here that's -3 over S plus 3 plus -2 over S plus 2. And then I do the inverse Laplace transform, and I get -3. And I think I screwed that up too, actually. -3, sorry, -3 times e to the -3t plus 2 to the -2t, and I guess it should be negative, right? Sorry. I'll have to double check that, make sure I did that right. But yeah, so that looks right. Oh yes, repeat how I got A and B. Yeah. So so you have the original function, which is s divided by s plus 3 times s plus 2. And this function I got actually by factoring. Well, in this case, I just changed the two. I just tweaked it to make it stable, basically. But initially, I had a transfer function that had a polynomial in the denominator. So I factored that polynomial. I got s plus 3 times s plus 2, and I want to decompose this into a plus s over s plus 3 plus b divided by s plus 2. And so to do that, I pretended as though I had started with this form, the a over s plus 3 plus b over s plus 2. Hopefully you can see my mouse cursor. Not sure if you can, but here, let me go out of presentation mode. I'm pretty sure you can see it now. Okay, good. So yeah, so if I had started with this, then, and let's say I wanted to make the denominator s plus 3 times s plus 2. See, doing that is easy because all you have to do in that case is take the second denominator and multiply it by the first numerator, and take the first denominator and multiply it by the second numerator, right? And then add those together. So if I had started with this, and it's pretty straightforward to go to that, right? It's just basically you're trying to get a common denominator. So that part is pretty straightforward. But then the question is, well, how do I solve for A and B? Well, to do that, I can delete both denominators on both sides of the equation because they're equal. So then I just end up with s equals a times s plus 2 plus b times s plus 3. And so I have to solve for A and B, except the problem here is I just have the one equation to work with here, but I have two unknowns. Now, in this case, I use a trick, and the trick is that because I have these two values of s that will make these partial, these two, s plus 2 and s plus 3, these sub-expressions, I have values of s that will make each of those sub-expressions 0, and there's two different values of s that'll make them 0. So in this case, if I make s minus 2, -2, then it will make the s plus 2 sub-expression 0, which then will be multiplied by a, which effectively kills a, drops a out of the equation. So then I end up, if that's the case, then I end up with -2, which is the value I assigned it to s to do that, equals b plus -2. Yeah. Oh, that's what I did wrong. Yeah, yes, thank you. Yeah, -2 plus 3. That's where I screwed that up. Thank you. -2 plus 3. And this, I think that was a copy paste there. And then a is -3 plus 2. Yeah, so there you go. So, let's see. So let me double check that. So -2 plus 3, that's from this guy, and -3. Yeah, -3 is put into s here, so it's -3 plus 2. So you end up with, the b. This is this expression here is 1, and this one's -1. So b over here is -2, right? And then this would be +3. That's right. Yeah, because this would give you a 1 and -3. Right. So A would be 3. All right. There we go. So we go over here, fix that over here. So we get 3 there, you get 3 here, and then finally, there we go. Okay. Yeah, and like I said, I'll double check. I'm going to double check this and make sure that I plotted the plot is correct. I have to replot it. But the point is that after you plot this, it's going to it's not going to rush off. The plot isn't going to have a limit to infinity. It's going to limit out on 0 or some constant, right? So in this case, you can see that the plot is stable. So this would be the impulse response. Now, if I were to simulate this in MATLAB and give it an impulse response, then I'll get the same plot. The difference is that by doing the inverse Laplace transform and then plotting it versus time myself, I effectively simulated this thing, right? I did this little simulation. I don't actually know how to simulate the step function or like a sinusoid. I don't even know how to do that. I that's something, MATLAB does that automatically, but I can do the simulation by hand for the impulse. So, and that's what I did. So speaking of the other simulations, the other inputs, so let's look at what MATLAB says about the step response. So if I give this guy a step, so these guys are correct, by the way, because see, the bugs I had with the signs had to do with when I went to the inverse Laplace. But now I'm just giving the original, the original S domain, which again, I just made it up. This was just an arbitrary function, but I plugged this in as my transfer function, and then I hit it with a step. And I looked at the result. So I have I did a scope here, and I did a scope here. So I did a scope on the input and a scope on the output of the transfer function. And you can see that the transfer function does this thing where it kind of goes up and then it comes back down and stabilizes. So so far I know that the impulse response was good, and the step response was good. And then just for the heck of it, I gave it a sinusoid too, just for good measure. That should be 2. And you can see that sinusoid looks good. You will notice though that the frequency is the same as the input and the output frequency are the same, but you can see that it did attenuate this guy. So the amplitude is not 1, it's 0.2. So it does have a it did attenuate the signal. Okay, so I mentioned that transfer functions can be combined together and can be used to compose a larger system. And this is the thing that's I think is really cool about this, is that basically if you want to take a transfer function and you want to feed it an input from another transfer function, you just multiply them. And so if you have them in this form, like for example, if this transfer function is y over u and this one is g over y, and then I multiply them, I get a sort of a composite transfer function that would be g over u, right? So it works out algebraically, but then if you multiply the S domain polynomials, or actually the fraction of polynomials that you'll get, it also works out. You end up with a and you can do this. You can scale this up as big as you want. In fact, what we were doing before was we were taking the Dirac or the impulse unit impulse, which has just a 1, and just multiplying against the transfer function that we synthesized. But in this case, you could take an arbitrary another transfer function and do the multiply. And so this is how you can build up larger systems. So and this is called a convolution operation. And so and then when you multiply, by the way, in the S domain, you're just multiplying polynomials. That's just like you would multiply any polynomial. So it's just becomes algebra, which is, I think, is pretty neat. If you look at this though, this actually is an open loop control system though already, because G in this case would be our plant and Y would be our controller. And then we would have some input from the user, which, you know, might look like a step function, for instance. Like if I was telling this, like I said, hey, robot, I need you to go forward by 1 meter. I need you to change your position by a meter. Then that input would basically be like a step function that would start at 0 and then would go to 1 meter. It would go into the controller. The controller would then send a signal to the robot, which would be the plant, and then we'd get some output. Now there would be, this would be open loop. You know, there would be no feedback in this case, but that would give me the open loop response. Okay, so now I'm going to switch gears for a minute and talk about how do we build a transfer function from a physical system, because that's the ultimate goal here, is to, like, if you're trying to control something like a robot, you need to be able to model the robot as a transfer function. Not the whole robot necessarily. You could do it piece by piece, and then, you know, you could model the motors, and then you could model the drivers into the motors, and then you could model, you know, there's different ways that you can compose these systems and build them up. But ultimately, we need to have a model of the physical system. Now, you could do it from kind of first principles, which is where you understand the physics of how the system works. So if it's like an RLC circuit, you can do that just by using the, you know, resistor, inductor, and capacitor equations. Or if it's physics, you're using forces, essentially. You know, you're just doing physics equations. There is another way, though. You can also use a data-driven approach, where you measure the response of the system by injecting different types of sinusoids into it, and then you can build the transfer function from that as well. That's called system identification. So there's two approaches. We're not going to talk about system identification in this class. I'm just going to show you kind of the first principles based approach, which is where you know, you build it from first principles. So so let me give you a really simple, this is a super simple one. So assume you have an object, and your goal is you want to move it. You just want to move it to a specific spot. So to do that, you want to apply a force, which we'll call U. And the force will literally be a force as you would have in physics. And then the output would essentially be the position of the object. So you can say, well, the force that I applied as an input to the system, as an input, we have to subtract the friction of moving that thing. The friction is calculated by giving us basically it gives us a negative force, which is proportional to some constant b multiplied by the velocity, the speed, y dot. Okay, so y is the position, y dot is a notation that just means that the first derivative, right? So it's the speed, the velocity. And then added those two things together gives me the final applied force of the object, which is going to be the mass of the object times the acceleration, which is y dot dot. Okay, so that's a super simple way to model just pushing something. You're applying an input force, it's got some friction, and you're trying to move it to a specific spot, y, right, which is the position. Ultimately, the idea is that I want to, you know, put it on this line. I want to move this puck, put it on the line. I want to get it right on the line, but I have to give it an exact amount of force to do that, which is the input. So so this type of an equation is in a really convenient form to get it in the Laplace, because it's literally just, you know, you've got u and y, you've got two time series you know, signals, right? And you've got y, one of them has a derivative and a double derivative. So all you got to do is just convert it to the S domain, and I even took out the S. You know, I just, or the sorry, I didn't put y of t here. I just said no y of S. I just took the y dot and I made it capital Y to signify that it's in the S domain, and then I multiplied it by S to signify that it is a derivative. And then this is a double derivative, so this is S squared, right? So this is capital U, which implied there it's capital U of S, but I don't have the of S because it's a shorthand. Subtract BSY equals MS squared Y, where B is a parameter that is the coefficient of friction, and M is the mass of the object that I'm pushing. Okay, and then so I can come up with so I took this guy and I brought the BSY over to the other side of the equation. I added that, and then I factored out Y as I did before, and then I want to know the transfer function. And again, I mean, this equation by itself is just a dynamics equation. If I want to actually come up with this notion of inputs and outputs, that's when I put it into a transfer function. And to do that, I just need to make sure that I've got one side of the equation that's y over u, because y is the output and u is the input. So I'm applying the input as the force, y is the position. And if I get into y over u, which I can do just by doing some algebra, so divide both sides here by u, and then divide both sides by ms squared plus bs, you end up with y over u equals 1 over ms squared plus bs. And that's my polynomial form, basically. That's the form that I want this to be in for a transfer function. Except I've got that m there. Usually the format is the leading power and the polynomial leading term would be 1, right? The leading coefficient would be 1. So to fix that, I can just divide the numerator and the denominator by m, right? So then I end up with 1 over m divided by s squared plus bsm. And then I can factor out s in the denominator, and I find out there that I have a pole at 0, and I have a pole at negative b over m. So I have one pole that's in the left-hand plane, and I have one pole that's on the 0. So this is an unstable this is an unstable system. As simple as it is, it's unstable because of that pole at 0. So yeah, so I'm going to go ahead and finish up here to give you 10 minutes to work on the quiz, because I didn't give you much time last time, and also I noticed that very few of you have looked at that quiz. So I want to give you a chance to look at that now, and I'll continue with this lecture on Monday. Any other questions before we go? Okay, great. Okay, then I will see you guys on Monday. Thank you. Oh, sure. Previous slide. Is that the previous slide? Yeah. Can you see it? Yeah, these slides are on Dropbox, by the way. I generally tweak these slides right before in the day before I lecture, so they're a little out of date, but I'll update them. I'm also going to fix those plots too, little typos with the signs on those constants. So I'll fix all that up and put the slides on Dropbox. But yeah, the slides are on Dropbox. They're just a little out of date right now, but I'll fix it up here within the next hour. Okay, thank you.